Continuity of rational and trigonometric functions. Hello, everyone. To begin today's lesson, let's first recall the foundation we have already built. In our previous sections, we established a very important rule, that polynomial functions are continuous everywhere. This means that no matter what value of x you choose, the graph of a polynomial is a smooth, unbroken curve. Building on that, we also discussed the algebra of continuous functions. Specifically, we learned that if you take two functions that are already continuous and combine them through addition, subtraction, or multiplication, the resulting function will also remain continuous. However, when we deal with division, we have to be more careful. The quotient of two continuous functions is indeed continuous, but there is one critical condition. The denominator must not be equal to 0. As we know, division by 0 is undefined, and this is precisely where a function typically loses its continuity. In this session, we are going to apply these fundamental rules to two specific categories of functions: rational functions and trigonometric functions. Over the next few slides, we will analyze how these rules help us determine exactly where these functions are continuous and where they might have breaks or discontinuities. 1. Rational functions. Now that we have established the general rules for the continuity of sums, products, and quotients, let us apply these principles to our first specific category: rational functions. Starting with the basics, what exactly is a rational function? Simply put, a rational function is defined as the ratio of two polynomial functions. To put this in mathematical terms, if we have two polynomial functions, which we can call p of x and q of x, then a function f of x is called a rational function if it is expressed as p of x divided by q of x. Now, let us analyze the continuity of these functions. First, we look at the continuity of the components. As we mentioned in the previous slide, every polynomial function is continuous for all real numbers. This means that both our numerator, p of x, and our denominator, q of x, are continuous everywhere on their own. Next, we apply the quotient rule. This rule states that the quotient of two continuous functions is also continuous, provided that the denominator is not 0. Therefore, we can conclude that a rational function is continuous at every single point within its domain. The only points of discontinuity occur specifically where the denominator, q of x, equals 0. To make this clearer, let us walk through a practical example. Consider the function f of x equals x plus 2, all divided by x minus 3. We will analyze this using a four-step process. In step 1, we identify the numerator as x plus 2 and the denominator as x minus 3. Since both of these are polynomials, they are continuous for all values of x. In step 2, we must find the values of x that would make the denominator 0. By setting x minus 3 equal to 0, we find that x equals 3. Step 3 is to determine the domain. Because the function is undefined when the denominator is 0, the domain includes all real numbers except for x equals 3. Finally, in step 4, we reach our conclusion. The function f of x is continuous at every point in its domain, which is represented by the intervals from -infinity to 3 and from 3 to positive infinity. However, it is discontinuous at x equals 3. Please keep this logic of checking the denominator in mind, as we will see a very similar pattern when we move on to discuss the continuity of trigonometric functions in the next slide. 2. Trigonometric functions. Now that we have analyzed rational functions, let us move on to the second part of our lesson: trigonometric functions. Trigonometric functions are essential tools in mathematics and science for modeling periodic phenomena, things that repeat in a regular cycle, such as sound waves or the rhythmic movement of a pendulum. However, it is important to note that their continuity depends entirely on how each function is defined. Let us begin with the sine and cosine functions. These are the most fundamental trigonometric functions. In terms of their properties, both sine of x and cosine of x are continuous for all real numbers x. The reasoning behind this is quite simple. If you observe their graphs, you will see they are smooth, unbroken waves that extend infinitely in both directions without any jumps, gaps, or holes. Next, we will examine the tangent function. The tangent function is defined as the ratio of the sine function to the cosine function. In other words, tangent of x equals sine of x divided by cosine of x. To perform a continuity analysis of tangent of x, we can apply the same logic we used for rational functions in the previous slide. First, we identify that both the numerator, sine of x, and the denominator, cosine of x, are continuous for all real numbers. By applying the quotient rule we discussed earlier, we know that tangent of x will be continuous wherever the denominator, cosine of x, is not equal to 0. So, where exactly does the function become discontinuous? We know from our study of the unit circle that cosine of x equals 0 whenever x is an odd multiple of pi over 2. Mathematically, we write this as x equals 2n plus 1, multiplied by pi over 2, where n is any integer. Consequently, our conclusion is that the function tangent of x is continuous at all points within its domain, but it is discontinuous at x equals 2n plus 1, multiplied by pi over 2. To help you visualize this, let us use a real-world analogy from signal processing in electronics. In this field, a pure sine wave represents a perfectly continuous signal. However, if a signal is clipped or interrupted, it becomes discontinuous. Similarly, the tangent of x function represents a signal that blows up, meaning it approaches infinity, as it nears those points of 2n plus 1, multiplied by pi over 2, which creates a physical break in the signal. Keep these points in mind, as we will see in the next slide that forgetting these specific conditions is a common mistake students make during exams. Common mistakes to avoid. Now that we have explored how to determine the continuity of both rational and trigonometric functions, let us discuss some common pitfalls to ensure you avoid these mistakes in your exams and assignments. First, let's address the issue of assuming global continuity. A very frequent error is to simply state that a rational function is continuous without specifying that it is continuous in its domain. As we saw in our previous discussion on rational functions, these functions are not continuous everywhere. They have breaks wherever the denominator equals 0. Therefore, you must always check the denominator and be precise with your wording. Secondly, be careful not to confuse the tangent function with the sine function. It is a common misconception that all trigonometric functions are continuous for all real numbers. While we established that sine and cosine are smooth, unbroken waves, remember that the tangent function, as well as secant, cosecant, and cotangent, is defined as a quotient. Because these functions involve division by other trigonometric functions that can equal 0, they inevitably have points of discontinuity. Finally, when you are defining the specific points where the tangent function is discontinuous, do not forget to mention that n is an integer. Because the tangent function is periodic and repeats infinitely, there are infinitely many points of discontinuity. If you omit the statement that n belongs to the set of integers, your mathematical description of the function's breaks remains incomplete. Keep these warnings in mind as we move forward to our final slide to summarize the key takeaways of this lesson. Key takeaways. To wrap up our lesson, let's review the key takeaways to ensure you have a solid grasp of these concepts. First, regarding rational functions, remember that a function f of x, defined as the ratio of p of x over q of x, is continuous at every point in its domain, except for the specific values where the denominator, q of x, equals 0. Next, moving on to trigonometric functions, as we observed in our previous analysis, both sine x and cosine x are continuous for all real numbers. Their smooth, unbroken wave patterns mean you will never find a jump or a hole in their graphs. However, for the tangent function, we must be more cautious. Tangent x is continuous everywhere except at x equals 2n plus 1 times pi over 2, where n is any integer. This is a direct result of the quotient rule we discussed, as the function breaks whenever the cosine component in the denominator becomes 0. Finally, the most important general rule to keep in mind is this. The continuity of a complex function can often be determined by breaking it down into simpler components, such as the polynomials or basic trigonometric functions we have covered, and then applying the fundamental algebra of continuous functions. This systematic approach will help you avoid the common mistakes we highlighted in the previous slide.